Hello there and welcome to the Twilight Archive, where quiet curiosity meets the deep mysteries that lie just beneath the surface of what we think we know. I'm your guide through the shadows of history, and tonight we're going to take a journey that begins in the warm waters of the Mediterranean Sea and ends somewhere you might not expect, at the very origins of the computer age. But we're not starting with silicon chips or punch cards. We're starting with something far older, far stranger, and in many ways far more mysterious. Picture this: corroded bronze fragments, crusted with 2,000 years of marine growth, sitting in a museum storage room in Athens. To most visitors, they'd look like nothing more than ancient junk, the kind of archaeological debris that fills the back rooms of museums around the world. Green and black lumps of metal, twisted and broken, telling no obvious story. Except that these particular lumps of corroded bronze have been quietly rewriting the history of human technology for over a century. They represent something that, according to everything we thought we knew about the ancient world, simply shouldn't exist. And yet there they are, as real and tangible as the screen you're watching right now. You see, we have this comfortable narrative about technological progress. We tell ourselves that human innovation moves in a steady upward line, stone tools to bronze tools to iron tools, simple machines to complex machines, mechanical devices to electronic ones. The past is primitive, the present is advanced, and the future will be even more so. It's a nice, clean story that makes sense of human history. But what happens when that story breaks down? What happens when you find something that doesn't fit, something that suggests our ancestors were capable of feats we never imagined? What happens when you discover that the ancient Greeks, famous for their philosophy and sculpture, were also building computers? That's exactly what we're dealing with tonight. Those corroded bronze fragments I mentioned? They're pieces of what we now call the Antikythera Mechanism, and it might just be the most important archaeological discovery you've never heard of. Or maybe you have heard of it, whispered references to an ancient Greek computer that pop up in documentaries and articles, usually accompanied by a lot of mystified head-scratching and vague gestures toward the mysterious wisdom of the ancients. But the real story of the Antikythera Mechanism is far more specific, far more remarkable, and far more unsettling than those mystical generalizations. Because this isn't about ancient wisdom or lost knowledge in some abstract sense. This is about precision engineering, mathematical sophistication, and technological capabilities that we didn't think existed until the Middle Ages at the earliest. We're talking about a device built sometime between 150 and 50 BCE, that's over 2,000 years ago, that could predict the positions of the sun, moon, and planets with extraordinary accuracy. A device that could forecast eclipses decades in advance. A device that tracked multiple calendar systems simultaneously and calculated the timing of athletic competitions and religious festivals. A device made of dozens of precisely crafted bronze gears, each one calculated to represent the complex movements of celestial bodies. In other words, we're talking about a computer. Not a metaphorical computer, not something that's computer-like in a loose sense, but an actual analog computer that processed astronomical data and produced predictions about the future state of the heavens. Built by people who supposedly didn't understand the wheel and axle. Now, you might be wondering how something this significant could remain relatively unknown. How does a device that fundamentally challenges our understanding of ancient technology stay tucked away in the margins of popular consciousness? Part of the answer is that the Antikythera Mechanism is genuinely difficult to understand. It's not like discovering a new species of ancient pottery or another variant of a known type of sculpture. This is a unique technological artifact that required researchers to essentially reverse engineer a machine that had been corroded beyond recognition, using techniques that didn't exist when it was first discovered. And part of the answer is that it's uncomfortable. The Antikythera Mechanism doesn't fit neatly into our narratives about the ancient world. It suggests that technological capability and scientific understanding can be lost as well as gained, that human progress isn't always linear, that entire civilizations can develop sophisticated technologies that then disappear without a trace. These are unsettling ideas that challenge some of our most basic assumptions about how human societies develop and how knowledge is preserved. But here's what makes the story even more remarkable. The Antikythera mechanism wasn't discovered by archaeologists carefully excavating an ancient site. It wasn't found in a royal tomb or a temple treasury. It was discovered by accident, by people who weren't looking for it, in circumstances that were equal parts adventure story and pure chance. If not for a Mediterranean storm in the spring of 1901, we might never have known that ancient Greek computers existed at all. And that raises another uncomfortable question. If this extraordinary device survived purely by chance, what else didn't survive? What other technological marvels lie corroded beyond recognition on the seafloor, or buried in landfills, or melted down for scrap metal over the centuries? The Antikythera mechanism might not be unique because it's the only device of its kind that was ever built. It might be unique because it's the only one we've found. So tonight, we're going to take apart this bronze riddle piece by piece. We're going to meet the sponge divers who stumbled upon it, the archaeologists who first recognized its significance, and the modern researchers who've spent decades coaxing its secrets from corroded metal using some of the most advanced scientific instruments on Earth. We're going to explore what the mechanism actually does, how it works, and what it tells us about the mathematical and engineering capabilities of ancient Greek civilization. But more than that, we're going to ask what the Antikythera mechanism means for our understanding of human technological development. Because this isn't just a story about an ancient computer. It's a story about the fragility of knowledge, the unpredictability of progress, and the humbling realization that our ancestors might have been far more capable than we ever imagined. So settle in, and let's dive beneath the waves of the Mediterranean, where a bronze machine has been waiting for over a century to tell us its story. Picture this: you're a sponge diver in 1901, and your world revolves around holding your breath and plunging into the deep blue waters of the Aegean Sea. For generations, your family has made their living this way, diving naked to depths that would terrify most people today, searching for the natural sponges that wealthy Europeans prize for their baths. It's dangerous work. Divers regularly suffer from what we now know as decompression sickness, and many don't make it to old age. But it's also honest work, and for the crew aboard the diving boat that autumn day, it seemed like just another season of following the sponges wherever the Mediterranean currents carried them. The divers were from the small Greek island of Symi, a place where the art of deep-water diving had been passed down through generations like a closely guarded family secret. These weren't casual swimmers, they were professionals who could dive to depths of 30 meters or more, staying underwater for minutes at a time while they carefully harvested sponges from the rocky seafloor. Their captain, Demetrius Kondos, had been doing this for decades, and he knew these waters like most people know their own neighborhoods. But on this particular day in early October, nature had other plans. A fierce storm was brewing, the kind that could turn the usually manageable Aegean into a churning, boat-swallowing monster. Kondos made the smart decision: they needed to find shelter, and fast. He steered his vessel toward the small, rocky island of Antikythera, wedged between the larger islands of Crete and the Peloponnese. You might recognize the name from maps today, but in 1901, it was just another uninhabited speck of land, useful mainly as a place to wait out bad weather. As the storm raged overhead, the diving crew found themselves with time to kill. And here's where luck, or maybe fate, decided to intervene. Elias Stadiatos, one of the more experienced divers, decided to explore the waters around their anchorage. Maybe he'd find some sponges to make the delay worthwhile. What he found instead would change our understanding of ancient technology forever. At a depth of about 45 meters, deeper than most recreational divers would ever venture even today, Stadiatos discovered something that initially made no sense at all. The seafloor was littered with what appeared to be human bodies, arms, legs, faces staring up at him through the blue-green gloom. For a heart-stopping moment, he must have wondered if he'd stumbled onto some kind of underwater graveyard, a mass tragedy that had somehow been hidden from the world above. But as he swam closer, his eyes adjusting to the filtered light, the truth became clear. These weren't bodies at all, they were marble statues, life-sized and remarkably preserved. Ancient Greek and Roman sculptures, scattered across the sandy bottom like pieces from some titan's chess set. He had discovered a shipwreck, and not just any shipwreck, but what appeared to be an ancient treasure ship, loaded with the kind of artifacts that museums around the world would kill for. When Stadiatos surfaced and gasped out his discovery to Captain Condos and the rest of the crew, you can imagine the excitement. These were practical men who knew the value of things, and they could recognize opportunity when they saw it. The storm might have trapped them here, but it had also led them to what was clearly the archaeological find of a lifetime. Condos himself made the next dive, and what he saw confirmed Stadiatos' incredible report. The wreck was extensive, clearly the remains of a large vessel that had gone down sometime in antiquity. Bronze and marble artifacts were scattered across a wide area of the seafloor, some buried in sand, others lying exposed to the gentle Mediterranean currents. There were fragments of pottery, bronze statues, jewelry, coins, the accumulated wealth of an ancient world, perfectly preserved in the deep. But perhaps most intriguing were the lumps of corroded bronze, shapeless masses that had been transformed by decades of saltwater into something resembling green rock. To the divers, these probably looked like the least valuable items on the wreck, formless chunks of oxidized metal that might have once been tools or weapons, now corroded beyond recognition. They collected them anyway, along with the more obviously valuable marble statues and bronze figures, but I doubt anyone suspected that these unremarkable lumps would prove to be the most significant discovery of all. The divers worked the site for months, making trip after trip to the bottom, carefully bringing up artifact after artifact. It was exhausting, dangerous work. Remember, this was 1901, long before scuba gear or modern diving equipment. Each dive was a held-breath gamble with the deep, and several of the divers were permanently injured by what we now know as decompression sickness. One diver died during the recovery effort. The sea, it seemed, demanded its payment for revealing its ancient secrets. Eventually, the Greek government got involved, as governments tend to do when priceless antiquities start surfacing. They organized a proper archaeological expedition, though by the standards we'd use today, it was still pretty rough and ready. The artifacts were transported to the National Archaeological Museum in Athens, where they joined the ranks of ancient treasures that scholars study and visitors gawk at. Among those artifacts were the corroded bronze lumps that the sponge divers had dutifully collected, even though they couldn't have known what they were looking at. These shapeless masses of green corrosion were catalogued, photographed, and then largely forgotten. After all, when you've got magnificent bronze horses and marble gods competing for attention, who's going to get excited about some corroded metal fragments? But as we'll see, those unremarkable lumps were about to reveal a secret that had been hidden under the waves for over 2,000 years. The sponge divers had inadvertently recovered the remains of a machine so sophisticated, so far ahead of its apparent time, that it would challenge everything we thought we knew about ancient Greek technology. They had found humanity's first computer, though it would take another century for us to realize what we were looking at. And so the bronze fragments sat in their museum cases, patient and silent, waiting for someone curious enough to look past the corrosion and ask the right questions. The man who would first glimpse the impossible was Valeos Staris, and he had the perfect temperament for the task. Picture him in 1902, hunched over a workbench in the dim light of the National Archaeological Museum of Athens. Staris was methodical, patient, the kind of scholar who could spend hours studying a fragment of pottery and emerge with insights about trade routes and daily life 2,000 years past. But what lay before him that day wasn't pottery. The bronze lumps from the Antikythera wreck had been sitting in storage for months, dismissed by most as unremarkable debris. They were corroded beyond easy recognition, fused together by centuries of seawater into what looked like nothing more than rocky concretions. You might walk past them in a modern museum and barely give them a second glance. But Starries had learned to see past surfaces. As he carefully cleaned away more of the marine encrustation, something caught his attention. There, embedded in the corroded mass, was an unmistakable shape, the tooth of a gear wheel. Not just one, but several, locked together in what could only be a mechanical system. Starries paused, cleaned his glasses, and looked again. The gears were still there. Now, we have to understand what this meant in 1902. The technological timeline that archaeologists accepted was clean and simple. Ancient civilizations had bronze, iron, maybe some basic pulleys and levers. Sophisticated geared mechanisms belonged to the medieval period at the earliest. What Starries was suggesting, that these corroded lumps contained complex machinery from the 1st century BCE, was like claiming to find a smartphone in a Viking grave. Starries documented what he saw with characteristic precision. He wrote that the fragments contained a gear with teeth like those of a modern clockwork mechanism. His colleagues were skeptical, to put it mildly. How could the ancient Greeks, brilliant as they were in philosophy and mathematics, have created something that resembled the inner workings of an 18th-century clock? The dismissal wasn't born from professional jealousy or academic politics. It came from a reasonable assessment of what seemed possible. We knew the Greeks had the wheel, but geared mechanisms required not just metalworking skills but a sophisticated understanding of mechanical advantage, gear ratios, and precision manufacturing. These weren't concepts we associated with the ancient world. But Starries had an advantage that pure theorizing couldn't match. He had the object itself. As weeks turned to months, he continued his painstaking examination. More gears emerged from the corrosion. Bronze wheels with carefully cut teeth, designed to mesh with extraordinary precision. The more he uncovered, the more impossible it became to dismiss what he was seeing. Think about the intellectual courage required here. Starries was essentially asking his peers to reconsider everything they thought they knew about ancient Greek technology. He was suggesting that somewhere in the classical world, craftsmen were creating mechanical computers while Julius Caesar was conquering Gaul. It was a claim that demanded extraordinary evidence, and Starries knew it. The fragments themselves told a story of remarkable sophistication. The gears weren't crude approximations of mechanical principles, they showed evidence of careful planning and precise execution. Someone had calculated exact gear ratios, planned the layout of multiple interconnected wheels, and manufactured bronze components to tolerances that wouldn't have been out of place in a Renaissance workshop. Yet for all his careful documentation, Starries couldn't fully explain what he'd found. The mechanism was too corroded, too fragmentary, to reveal its complete purpose. He could prove that sophisticated gears existed in the ancient world, but he couldn't answer the obvious next question: what were they for? This uncertainty gave his critics room to maneuver. Some suggested the gears might be from a much later period, somehow mixed in with genuinely ancient artifacts. Others proposed that while the gears were ancient, they represented a unique aberration, perhaps a single genius craftsman whose techniques died with him. The idea that this represented a broader tradition of Greek mechanical engineering was still too much to accept. What's fascinating is how the academic establishment's initial resistance reveals our own assumptions about technological progress. We tend to think of innovation as a steady upward climb, with each generation building systematically on the last. The possibility that ancient civilizations might have achieved sophisticated technologies that were then lost challenges this comfortable narrative. Starries continued his work with remarkable persistence. He made detailed drawings, took careful measurements, and slowly built a case that couldn't be ignored. By 1906, he had identified the remains of what he called a mechanical calculator designed for astronomical purposes. He was closer than anyone would get for another 50 years. The scientific community's response was a mixture of grudging acceptance and continued skepticism. Yes, the gears were real. Yes, they were ancient. But the full implications of what that meant would take decades to sink in. Stars had opened a door to a different understanding of the classical world, but few were ready to walk through it. Looking back, we can see that Stars was working at the very edge of what 19th-century archaeology could accomplish. He had the right instincts and the right methods, but the tools he needed, X-ray photography, computed tomography, advanced metallurgical analysis, wouldn't be available for generations. He was like an astronomer trying to study distant galaxies with the naked eye. He could see that something remarkable was there, but the details would have to wait. What strikes me most about Stars' story is his willingness to trust his observations over his expectations. The gears were impossible according to everything he'd been taught about the ancient world, but they were undeniably there. That kind of intellectual honesty, the willingness to let evidence challenge theory rather than the other way around, is what separates genuine discovery from academic dogma. By the time Stars published his findings, he had fundamentally altered our understanding of Greek technological capability. He hadn't solved the mystery of what the mechanism did or how it worked, but he had established beyond doubt that it was something extraordinary. The bronze gears were real, they were ancient, and they represented a level of sophistication that demanded explanation. And so the Antikythera Mechanism entered the historical record not as a solution, but as a question that would haunt researchers for the next century. What could drive ancient craftsmen to create such intricate machinery? What knowledge were they trying to capture in bronze and gear teeth? To answer those questions, we need to step back and understand how the Greeks saw the universe itself. Picture yourself standing in the marble courtyard of the Academy in Athens, sometime around 350 BCE. The sun is setting, painting the columns in warm amber light, and you can hear the gentle murmur of philosophers debating under the olive trees. Now look up at that darkening sky. What do you see? If you're like most people today, you see scattered points of light, maybe the bright disk of the moon, perhaps a planet or two if you know where to look. Beautiful, certainly, but also somewhat random. Chaotic, even. But if you were an ancient Greek, particularly one trained in the mathematical traditions that flowed from Pythagoras through Plato and into the hands of brilliant minds like Hipparchus, you would see something entirely different. You would see a machine. Not a machine in our modern sense of pistons and circuits, but something far more elegant. The Greeks looked at the night sky and saw the universe as a vast, interconnected clockwork where every celestial body moved according to precise mathematical laws. They called this concept the harmony of the spheres, and it wasn't just poetic metaphor, it was serious science. Think about what this means for a moment. We know today that the ancient Greeks had no telescopes, no satellites, no computer models. Yet somehow, through pure observation and mathematical reasoning, they developed a model of cosmic mechanics that was remarkably sophisticated. They tracked the wandering paths of planets, literally a wanderers if in Greek, and noticed that beneath their seemingly erratic movements lay deeper patterns. The key insight, and this is where we start to understand the true genius behind the Antikythera Mechanism, was that these patterns could be predicted. Not through divine prophecy or mystical revelation, but through mathematics. The Greeks discovered that if you watched the sky carefully enough, for long enough, you could discern cycles within cycles, wheels turning within wheels. Let's take the moon as our first example. You've probably noticed that the moon goes through phases, new moon to crescent to full and back again. The Greeks measured this cycle precisely, 29.5 days, give or take. But they also noticed something else. The moon doesn't just change phases, it also changes position relative to the background stars. Sometimes it's high in the sky during winter, sometimes low. Sometimes it rises with certain constellations, sometimes with others. This led them to discover what we now call the lunar month versus the sidereal month. The lunar month, the time from new moon to new moon, is about 29.5 days. But the time it takes for the moon to return to the same position relative to the stars is slightly different, about 27.3 days. Why? Because as the moon orbits Earth, Earth itself is moving around the sun, so the moon has to catch up a little each month to align with the sun again. Now imagine you're a Greek astronomer trying to keep track of this. You need to predict not just when the next full moon will occur, but exactly where in the sky it will be. You start to realize that you need multiple cycles running simultaneously, one gear for the moon's phases, another for its position among the stars, perhaps another for how high or low it appears in different seasons. But the moon was just the beginning. The Greeks were also tracking Mercury, Venus, Mars, Jupiter, and Saturn. Each planet had its own complex dance across the sky, its own set of nested cycles that needed to be understood and predicted. Mars, for instance, has a particularly puzzling habit of occasionally appearing to move backward against the background stars, what we call retrograde motion. How do you build a mechanical model of something that sometimes goes backward? The Greeks solved this through pure geometric brilliance. They proposed that planets move in circles, but those circles themselves move along larger circles. It's like a carnival ride where you're spinning on a small wheel that's attached to a larger wheel that's also spinning. Sometimes, depending on where you are in both rotations, you appear to move backward relative to someone watching from the ground. This epicycle theory, refined over generations of Greek astronomers, provided a mechanical explanation for planetary motion that could be translated directly into bronze gears. Each epicycle becomes a set of meshing wheels, each wheel rotating at precisely the right speed to recreate the observed motions of the actual planets. But here's where the Greek conception of the cosmos becomes truly remarkable. They weren't content to just track individual celestial bodies. They wanted to understand how everything fit together, how all these cycles meshed into one grand cosmic machine. They discovered that eclipses followed predictable patterns, the Saros cycle we mentioned earlier. They found that certain planetary alignments repeated after specific intervals. They even noticed that their calendar needed regular adjustments to stay synchronized with the seasons. Imagine the intellectual leap required here. These ancient thinkers looked at the bewildering complexity of the night sky and said, "This isn't chaos. This is clockwork." And then, and this is the truly staggering part, they decided to build a working model of that clockwork. This wasn't just about predicting eclipses or tracking planet positions, though those were certainly practical applications. This was about capturing the very structure of reality in a device small enough to hold in your hands. The Antikythera Mechanism, we're beginning to understand, was nothing less than a bronze model of the entire cosmos as the Greeks understood it. Every gear ratio in the mechanism corresponds to an observed astronomical relationship. The 19-year Metonic cycle, which synchronizes lunar and solar calendars, becomes a specific set of gear teeth, 235 to 19, to be precise. The 76-year Calippic cycle, a refinement of the Metonic cycle, gets its own mechanical representation. Even the 4-year Olympic cycle finds its place in the bronze wheels. What we're looking at, then, isn't just an ancient calculator. It's a physical embodiment of how an entire civilization understood the universe. It's Greek cosmology made manifest in metal, philosophy transformed into physics, mathematics given mechanical form. And that raises a fascinating question. If the Greeks could conceive of the cosmos as a clockwork mechanism 2 millennia before we developed actual clockwork, what does that tell us about the relationship between human understanding and technological capability? Were they limited by their tools, or by something else entirely? And here's where our story takes a fascinating turn into what we might call accidental archaeology. Because for the first half of the 20th century, the Antikythera Mechanism sat in storage at the National Archaeological Museum in Athens, looking for all the world like a collection of corroded, worthless lumps. Imagine you're a museum curator in 1950, looking at these bronze masses encrusted with marine growth and oxidation. They don't look like anything remotely technological. They look like ancient garbage that someone should probably throw away. But science, as we know, has a wonderful way of seeing through surfaces. In the 1950s, a British science historian named Derek de Solla Price became fascinated by these forgotten fragments. Price wasn't content to simply accept that the Greeks couldn't have built complex machinery. He wanted to look inside these corroded lumps, and fortunately for us, he had access to something the original discoverers didn't: X-ray technology. When Price first X-rayed the fragments in 1959, what he saw changed everything. There, ghostly and beautiful against the photographic plate, were the unmistakable silhouettes of gear wheels. Not just one or two gears, but an intricate network of bronze cogwheels, some as small as coins, others larger than your palm. You have to picture this moment: Price staring at these X-ray images, realizing that he was looking at mechanical engineering from ancient Greece that shouldn't have existed for another 1,000 years. But X-rays, revolutionary as they were, could only show us so much. They revealed that gears were there, yes, but they couldn't tell us how they connected to each other, how they moved, or what calculations they performed. It was like trying to understand a symphony by looking at the shadows of instruments on a wall. You know there's music there, but you can't hear the melody. So we waited. We waited for technology to catch up with our curiosity, and slowly, decade by decade, it did. By the 1970s, researchers had access to better X-ray equipment that could peer deeper into the mechanism's interior. Linear tomography allowed them to see layers within the bronze masses, revealing gear trains that seemed to snake through the device like mechanical DNA. Then came the 1990s, and with them, computed tomography, CT scans. The same technology we use to peer inside human bodies without cutting them open could now peer inside ancient artifacts without damaging them. Michael Wright, a former curator at the Science Museum in London, became obsessed with applying this technology to the mechanism. Wright spent years analyzing CT scans, building detailed drawings of how the gears might have connected, even constructing working replicas based on his interpretations. But it was in the early 2000s that the real breakthrough came. A research team led by Tony Freeth, working with companies like X-Tech Systems, developed a specialized form of CT scanning called microfocus X-ray tomography. This wasn't your hospital CT scanner. This was precision imaging that could reveal details smaller than the width of a human hair. When they applied this technology to the Antikythera fragments, something extraordinary happened. For the first time, researchers could see not just the gears, but the inscriptions on them. They could read text that had been hidden beneath layers of corrosion for 2,000 years. Imagine that, words written by ancient Greek craftsmen, instructions and calculations, suddenly becoming visible again through the magic of modern physics. The scans revealed something that took everyone by surprise. This wasn't just a collection of random gears thrown together by some ancient tinkerer. This was precision engineering. Every gear ratio had been calculated with mathematical precision. Every wheel was positioned exactly where it needed to be to perform its specific function. We're looking at a level of mechanical sophistication that wouldn't appear in Europe again until the great astronomical clocks of medieval cathedrals. As the scanning technology improved, so did our understanding. Each new technique revealed another layer of complexity. Surface scanning showed us the external features of the fragments. Volume rendering let researchers virtually disassemble the mechanism, examining each gear individually. Polynomial texture mapping revealed inscriptions that were invisible to the naked eye, texts that told us how the ancient Greeks actually used this device. But here's what really gets me about this process of technological revelation: it's been a collaboration across centuries. Ancient Greek engineers encoded their knowledge in bronze. Modern engineers decoded that knowledge using particle accelerators and computer algorithms. We've been having a conversation with the past, using technology as our translator. And the conversation isn't over. Even now, researchers are developing new techniques to peer deeper into the mechanism's secrets. They're using artificial intelligence to analyze the gear patterns, looking for clues about missing components. They're applying techniques borrowed from materials science to understand how the bronze was cast and shaped. Some teams are even using virtual reality to walk through digital reconstructions of the complete mechanism, experiencing it as its original users might have. Each technological advance has revealed new layers of sophistication in this ancient device. What began as mysterious corroded lumps has revealed itself to be one of the most complex mechanical computers ever created in the ancient world. But every answer has raised new questions. How many of these mechanisms existed? Were they common, or was this a unique creation? And most tantalizing of all, what other ancient technologies might be waiting for our tools to become sophisticated enough to see them? You see, the story of the Antikythera mechanism isn't just about ancient Greek engineering. It's about the evolution of human curiosity and our tools for satisfying that curiosity. 50 years ago, these fragments looked like worthless corrosion. Today, they look like the remnants of an ancient computer. What will they look like 50 years from now, when we have scanning technologies we can't even imagine yet? And that raises a profound question about archaeological discovery itself. How much of the past is invisible to us not because it doesn't exist, but because we don't yet have the tools to see it? And that raises a profound question about archaeological discovery itself. How much of the past is invisible to us not because it doesn't exist, but because we don't yet have the tools to see it? As the layers of corrosion slowly gave way to X-rays and CT scans, what emerged was something that transformed our understanding of what the Antikythera mechanism actually was. We weren't looking at a simple astronomical calculator. We were looking at a portable cosmos, a bronze universe that held the intricate dance of time itself within its gears. Imagine you're living in ancient Greece, around the 1st century BCE. Your world isn't governed by our modern calendar with its arbitrary weekends and standardized months. Instead, your entire life revolves around cycles that connect you directly to the movements of the heavens. When do you plant your crops? When the stars tell you. When do you celebrate the festivals that honor your gods? When the moon reaches the proper phase. When do the Olympic Games begin? When the celestial calculations align just right. This is where the Antikythera mechanism reveals its true genius. It wasn't just tracking the sun and moon for academic curiosity. It was encoding the entire rhythm of Greek civilization into bronze gears. Let's start with something we can wrap our minds around: the Olympic Games. You might be wondering how ancient athletic competitions connect to astronomical machinery. Well, the Olympics weren't just sporting events. They were sacred festivals held every 4 years in honor of Zeus, and their timing had to be perfect. The mechanism contained a dedicated dial that could calculate exactly when these games would occur, years or even decades in advance. Think about that for a moment. Greek engineers built a computer to predict when athletes would gather to throw javelins and race chariots. But the Olympics were just one thread in a much more complex tapestry. The mechanism also tracked what scholars call the Metonic cycle, a 19-year pattern that reconciles the lunar and solar calendars. This might sound abstract until you realize what it meant for daily life. Greek months followed the moon, but their seasons followed the sun. Without a way to synchronize these cycles, your calendar would drift completely out of alignment with reality. festivals supposedly held in spring would gradually migrate to winter. The mechanism solved this problem with mathematical precision, using gear ratios that automatically corrected for the accumulating errors. And then there were the eclipses. We'll explore this in more detail shortly, but imagine the psychological impact of being able to predict when the sun would go dark or when the moon would turn blood red. In a world where such events were often interpreted as omens from the gods, having advance warning would have been an extraordinary form of power. The researchers who've spent decades studying these bronze fragments have identified multiple calendar systems embedded within the mechanism. There's evidence of the Egyptian calendar, with its 365-day year. There's the Greek lunar calendar with its complex intercalations. Some scholars believe they found traces of Babylonian astronomical periods as well. This wasn't just a Greek device, it was a synthesis of the ancient world's accumulated knowledge about time and the heavens. You have to understand, this level of integration was staggering for its time. We're talking about a device that could simultaneously track multiple overlapping cycles, each with different periods and requirements. The main solar year. The lunar months. The planetary positions. The eclipse cycles. The festival calendar. The Olympic schedule. All of this information was encoded in the precise ratios between bronze gear wheels, each one cut and positioned with remarkable accuracy. But here's what makes this even more extraordinary. The mechanism wasn't just a passive calculator, it was interactive. You could turn the main crank and watch as all these different cycles advanced together, maintaining their proper relationships across months, years, even centuries. It was like holding a working model of time itself. The inscriptions that researchers have painstakingly deciphered from the corroded surface read like an ancient user's manual. They describe how to operate the device, how to interpret its various dials, and what the different positions mean. These weren't technical specifications written for other engineers, they were instructions for users who needed to understand when to plant crops, when to schedule religious ceremonies, when to expect eclipses that might affect important decisions. What strikes me most profoundly about this is how it reveals the ancient Greek relationship with time. We tend to think of time as something that flows uniformly, marked by the steady tick of digital clocks. But the Greeks lived within multiple interwoven cycles, each with its own rhythm and significance. The mechanism didn't just track these cycles, it made their hidden connections visible and predictable. Think about the craftsmen who built this device. They had to understand not just mechanical engineering, but astronomy, mathematics, and the complex religious calendar that governed Greek society. They had to translate abstract astronomical periods into precise gear ratios, then manufacture bronze wheels with tolerances that would maintain accuracy over decades of use. They were creating what we might call today a specialized computer, designed for a very specific but incredibly important purpose. And this brings us to something fascinating that researchers have discovered in recent years. The mechanism appears to have been designed not just for Greek users, but as a kind of universal calendar computer. The inclusion of multiple calendar systems suggests it could serve travelers, traders, or scholars who needed to navigate between different cultural systems of timekeeping. It was portable knowledge, centuries before the printing press made such information widely accessible. As we examine these bronze fragments today, we're essentially looking at humanity's first attempt to create what we might recognize as a personal computer, a device that takes complex calculations and makes them accessible to individual users through a mechanical interface. The gears are our processors, the dials are our displays, and the inscriptions are our user manuals. But there's something else hidden within these bronze wheels that's even more remarkable than the calendars and cycles we've discussed so far. The mechanism could peer into the future and predict one of the most dramatic celestial events ancient people ever witnessed. And understanding how it accomplished this reveals just how sophisticated Greek astronomy had become, centuries before we gave them credit for such knowledge. But here's where our story takes on an almost heartbreaking dimension. When we talk about the Antikythera Mechanism's sophistication, we're describing something that exists largely in fragments. Only about 1/3 of the original device survived its centuries underwater, and what remains is so corroded that much of it looks more like a barnacle-encrusted rock than precision engineering. Yet from these broken pieces, researchers have managed to identify at least 37 meshing bronze gears. 37. Think about that for a moment. We're not talking about a simple clockwork toy or a basic astronomical calculator. This was a machine of extraordinary complexity, and we're seeing only the surviving remnants of what was once a complete mechanical universe. Each of those gears was cut with remarkable precision. When researchers examined the teeth under high magnification, they found evidence of careful filing and shaping. Someone, we don't know who, sat with bronze blanks and hand tools, calculating gear ratios that would need to mesh perfectly to track the movements of celestial bodies across years, decades, even centuries. The level of craftsmanship rivals anything produced in medieval Europe 1,000 years later. But it's not just the craftsmanship that astounds. It's the mathematics embedded in those gear ratios. Take the relationship between the Sun and Moon gears, for instance. The ancient Greeks knew that the Moon completes roughly 12.37 cycles relative to the Sun each year. That's not a clean, simple number to work with mechanically. How do you build that ratio into bronze gears? The mechanism's creators solved this through what we might call mechanical fractions. They used compound gear trains, gears driving other gears, to approximate complex astronomical ratios with remarkable accuracy. The main solar gear has 64 teeth, which meshes with a 38-tooth gear, giving us a ratio that, when combined with other gear trains, produces the correct relationship between solar and lunar months. Here's what makes this even more impressive. The Greeks didn't have our modern understanding of planetary mechanics. They didn't know that Earth orbits the Sun, or that gravitational forces govern celestial movements. They were working from careful observation and geometric models, yet they encoded astronomical knowledge into this machine that remained accurate for centuries. Consider the challenge facing the mechanism's unknown creator. You need to track not just the Sun and Moon, but Venus, Mars, Jupiter, Saturn. Each moves at its own pace across the sky, following its own complex pattern. Venus, for example, appears as both morning and evening star, vanishing and reappearing in cycles that repeat every 584 days. How do you encode that into meshing gears? The answer lies in what researchers call the gear trains, carefully calculated sequences of interlocking wheels that transform the simple rotation of a main crank into the complex motions needed to track each celestial body. It's mechanical programming, written in bronze rather than code. We can trace some of these calculations back to specific astronomical knowledge. The mechanism incorporates the metonic cycle, a 19-year period after which the phases of the Moon repeat on the same dates. It also tracks the Ecliptic cycle, a refinement that spans 76 years. These weren't abstract mathematical concepts to the Greeks. They were practical tools for organizing religious festivals, agricultural activities, and civic life. But perhaps most remarkably, recent analysis has revealed that the mechanism wasn't just following standard astronomical tables. The gear ratios suggest its creators had access to observational data of extraordinary precision. The lunar motion encoded in the device accounts for the fact that the Moon's orbit isn't perfectly regular. It speeds up and slows down in a pattern that wouldn't be fully explained until Newton's work on gravitational mechanics. How did they know this? We can only speculate, but it suggests generations of careful observation, mathematical refinement, and mechanical innovation. Someone was watching the skies with remarkable dedication and accuracy, recording variations that most ancient astronomers never noticed. The precision becomes even more striking when you consider the manufacturing constraints. Bronze is not an easy material to work with this level of detail. It's harder than gold or silver, but softer than iron. The gear teeth had to be shaped individually, filed by hand to mesh smoothly with their neighbors. A single miscalculation, a gear tooth slightly wrong, and the entire mechanism would jam or produce inaccurate results. Yet somehow, it worked. For how long, we can't be certain, but the wear patterns on surviving gears suggest the mechanism was actively used, not just a demonstration piece or luxury item gathering dust in some wealthy Roman's villa. This raises questions that extend far beyond a single device. If Greek craftsmen could produce mechanical computers of this sophistication, what else might they have created? We know from historical sources that ancient engineers built automated theaters, self-opening temple doors, even primitive steam engines. But these were curiosities, marvels designed to impress rather than practical tools. The Antikythera Mechanism is different. It was built to solve real problems, predicting eclipses, calculating festival dates, tracking planetary positions. It represents applied technology at a level we didn't think existed in the ancient world. And yet we have only fragments. Imagine what we've lost. Not just other copies of this specific device, though there were almost certainly others, the mechanism shows evidence of being part of a tradition, not a one-off invention. But think about all the other mechanical innovations that might have existed, devices that didn't happen to sink in exactly the right conditions to preserve even partial remains. The bronze gears we can study today are like scattered pages from a lost library of ancient technology. Each tooth, each gear ratio, each corroded fragment tells us something about minds we never knew existed, Greek engineers and astronomers who understood far more about mechanical computation than we ever imagined possible. As researchers continue piecing together these fragments, each new discovery raises the bar for what we thought ancient technology could achieve. But it also raises a more unsettling question: if they could build this, what else did they build that we'll never recover? And more importantly, how did such sophisticated knowledge simply disappear, leaving barely a trace in the historical record until chance and storm winds revealed it again, over 2,000 years later? Now let's talk about something that would have seemed like magic to anyone watching it work. Picture yourself in ancient Greece, perhaps in the Agora of Athens or the markets of Rhodes. A merchant or scholar approaches with what looks like an ornate bronze box. He turns a few dials, makes some calculations, and then announces with absolute confidence that 18 months from now, on a specific day, the sun will disappear from the sky in the middle of the afternoon. Would you believe him? The Antikythera Mechanism could do exactly that. And here's what makes this truly extraordinary: it wasn't guessing. It was calculating. Eclipses terrified ancient peoples. When the sun suddenly vanished or the moon turned blood red, it was often interpreted as the anger of gods, a portent of war, or the end of the world itself. But certain scholars, particularly those influenced by Babylonian astronomy, understood that eclipses followed patterns. They weren't random acts of divine wrath. They were as predictable as the tides. The key was something called the Saros cycle. The Babylonians had discovered that eclipses repeat in a very specific pattern every 223 lunar months, which equals about 18 years, 11 days, and 8 hours. If you witnessed a solar eclipse on a particular day, you could be confident that another very similar eclipse would occur exactly one Saros cycle later. The catch? It would be visible from a different part of Earth, shifted by about 8 hours of longitude because of those extra 8 hours in the cycle. Now, knowing this pattern is one thing. Actually using it to predict eclipses decades in advance? That requires serious mathematical sophistication. And transforming that mathematical knowledge into a physical device that anyone could operate? That's engineering genius. When researchers first identified the eclipse prediction capabilities of the Antikythera Mechanism, they found something remarkable embedded in those corroded bronze gears. The device contained what we now call the Saros dial, a carefully constructed spiral that could track this 223-month cycle with extraordinary precision. But it didn't stop there. The mechanism also incorporated the exoligmos cycle, which is 3 Saros periods or about 54 years. This longer cycle brought eclipse predictions back to roughly the same geographic location. Think about what this means practically. You could walk up to this device, input a specific date, and it would tell you whether an eclipse was coming. More than that, it could distinguish between different types of eclipses, solar or lunar, total or partial. The dials would show you not just when, but what kind of celestial drama was approaching. But here's where things get really interesting. The mechanism didn't just predict eclipses mechanically, it actually modeled the underlying astronomy. The device incorporated what we call the anomalistic lunar cycle, accounting for the fact that the moon's orbit isn't perfectly circular. Sometimes the moon is closer to Earth, sometimes farther away, and this affects both the timing and appearance of eclipses. The ancient Greek craftsmen who built this machine understood orbital mechanics well enough to encode these subtle variations into bronze gears. We know from historical records that eclipse predictions were serious business in the ancient world. The Greek historian Herodotus tells us about a battle between the Lydians and the Medes that was interrupted by a solar eclipse. Both armies, interpreting this as a divine sign, immediately made peace. But imagine if one side had possessed an Antikythera mechanism. They would have known the eclipse was coming. They could have used that knowledge strategically, timing their movements or even using the predictable terror of their enemies to their advantage. This raises a fascinating question about the mechanism's purpose. Was it purely scientific, a device for scholarly study of the heavens? Or did it have more practical, even political applications? In a world where priests and rulers claim to interpret divine will, having a machine that could predict celestial events might have been the ultimate source of power and authority. What really strikes me about the eclipse prediction feature is how it bridges two different worlds of knowledge. On one hand, you have the abstract mathematical understanding developed by Babylonian astronomers over centuries of careful observation. These were pure numbers, cycle lengths, period ratios, geometric relationships. But then some brilliant craftsman working in bronze, found a way to make those numbers physical. They created gears with tooth counts that precisely matched the astronomical ratios. They designed dials that could display the results in a way that anyone could read. This transformation from abstract to concrete, from mathematical theory to mechanical reality, represents one of humanity's great intellectual achievements. It's the same conceptual leap that leads from understanding the mathematics of flight to building an actual airplane, or from knowing the equations that govern electricity to constructing a working computer. And here's something that gives me chills when I think about it. The eclipse predictions embedded in this device were accurate. Modern researchers have tested the mechanism's calculations against known historical eclipses, and the results match. A device built over 2,000 years ago, using only the astronomical knowledge available to ancient Greeks, could predict celestial events with an accuracy that wouldn't be surpassed until the development of modern astronomy. But perhaps most remarkably, the mechanism could look both forward and backward in time. You could turn its dials to explore eclipses from the past or peer decades into the future. In a very real sense, this bronze computer allowed its users to travel through time, to step outside the present moment and see the long rhythms of the cosmos. When we talk about the Antikythera mechanism as humanity's first computer, this is exactly what we mean. It took complex calculations that would have required tremendous time and expertise to perform by hand, and it automated them. It made sophisticated astronomical knowledge accessible to anyone who could turn a dial and read a scale. This eclipse predicting capability transforms our understanding of what was possible in the ancient world. It suggests that somewhere, perhaps in workshops we'll never discover or in texts that have long since crumbled to dust, there existed a sophisticated tradition of precision engineering and applied mathematics that we're only now beginning to glimpse. And that glimpse raises yet another question that will follow us through the rest of our exploration tonight. If they could build a computer to predict eclipses, what other seemingly impossible technologies might they have created? What happened next is one of the most profound technological silences in human history. The Antikythera Mechanism, with its intricate bronze gears and sophisticated astronomical calculations, simply vanished from the historical record. Not just the device itself, the entire knowledge base that created it seems to have evaporated. We know this because when we trace the development of mechanical computation through history, there's a gap that spans over 1,000 years. The next devices we find that even approach the mechanism's complexity don't appear until the medieval Islamic world, where brilliant astronomers and engineers like Al-Jazari began building elaborate water clocks and astronomical computers in the 12th and 13th centuries. These Islamic devices were marvels in their own right: tower clocks with moving figures, astrolabes that could calculate prayer times, mechanical calendars that tracked the Islamic lunar year. But even these sophisticated machines operated on simpler principles than what the Greeks had achieved 12 centuries earlier. It wasn't until the great mechanical clocks of medieval Europe, the astronomical clock of Prague, completed around 1410, or the intricate clockwork of Giovanni Dondi's Astrarium from the 1360s, that we see technology beginning to match what that anonymous Greek craftsman had accomplished in the 1st century BCE. And even then, these were massive installations, tower-sized mechanisms that required teams of craftsmen to maintain. The Antikythera device was portable, handheld, a personal computer for the cosmos. This raises an unsettling question that archaeologists and historians have been grappling with for decades. If the Greeks could create something this sophisticated, what else could they have made? What other technologies flourished briefly and then disappeared, leaving no trace except perhaps a corroded fragment on some distant seafloor? Consider what we know about ancient Greek engineering from other sources. They built the Parthenon with tolerances measured in millimeters. They created the screw pumps of Archimedes, complex siege engines that could hurl stones across vast distances, and intricate architectural devices like the crane systems that lifted massive marble blocks hundreds of feet into the air. Hero of Alexandria, writing in the 1st century CE, described steam engines, automated temple doors, and mechanical theaters with moving figures, technologies that sound almost science-fictional until you realize the mathematical and engineering knowledge was already there. But here's what makes the silence even more mysterious. The mechanism wasn't created in isolation. The precision of its gears, the accuracy of its calculations, the sophistication of its design, all of this points to a mature technology, something that had been refined over generations. You don't create a device this complex as your first attempt. There must have been earlier versions, simpler prototypes, entire workshops devoted to this kind of precision engineering. So where did it all go? Why did this technological tradition simply vanish? Part of the answer lies in the fragility of knowledge itself. Ancient technologies were passed down through apprenticeship systems, master craftsmen teaching selected students the secrets of their trade. There were no instruction manuals, no patent offices, no universities dedicated to preserving technical knowledge for posterity. When a workshop closed, when a master died without passing on his knowledge, when political upheaval scattered the craftsmen, entire technological traditions could disappear in a single generation. We see this pattern repeated throughout history. The Romans perfected a concrete formula that allowed them to build structures like the Pantheon, with its massive unreinforced dome that still stands today. The recipe for that concrete was lost for over 1,000 years, only recently reverse-engineered by modern scientists who discovered that Roman builders were incorporating volcanic ash in ways that actually made their concrete stronger with age. Damascus steel, famous for its legendary sharpness and distinctive watered patterns, was produced for centuries before the knowledge vanished completely. Modern metallurgists are still trying to fully understand how those medieval smiths achieved what they did. But the Antikythera mechanism represents something even more profound than lost recipes or forgotten techniques. It represents an entire approach to understanding and manipulating the physical world that seems to have vanished without a trace. The device doesn't just demonstrate mechanical skill, it shows a way of thinking about complex systems, about encoding mathematical relationships in physical objects, about creating interfaces between human curiosity and cosmic knowledge. What other devices might have embodied this same approach? Archaeological evidence suggests the Greeks were experimenting with steam power, automated machinery, and precision optics. Archimedes supposedly created mirrors that could focus sunlight to burn ships at a distance, a claim that sounded like pure myth until modern experiments demonstrated it was entirely feasible with the mathematics and materials available at the time. And remember, the mechanism we have is damaged, corroded, incomplete. It represents perhaps 1/3 of the original device. What capabilities did we lose with those missing pieces? What other dials, what other calculations, what other windows into ancient Greek scientific thinking corroded away on that Mediterranean seafloor? The silence becomes even more poignant when we consider how this knowledge might have developed if it had survived. Imagine if the tradition of precision mechanical computation had continued unbroken from ancient Greece through the medieval period. Where might human technology be today if we'd had an additional 1,000 years of continuous development in this particular direction? It's a sobering reminder of how precarious human knowledge really is. We like to think of technological progress as inevitable, as a steady march forward that can only be temporarily interrupted. But the Antikythera mechanism tells a different story. It shows us that entire technological civilizations can rise and fall, leaving behind only fragments for future archaeologists to puzzle over. Which brings us to our modern moment, where we're using the most advanced technology in human history, particle accelerators, AI systems, quantum computers, to understand what our ancestors achieved with bronze and mathematical insight over 2,000 years ago. There's something both humbling and thrilling about that collaboration across millennia, ancient Greek genius reaching forward to meet contemporary scientific curiosity. And that collaboration is revealing secrets that are reshaping our understanding not just of ancient technology, but of the fundamental nature of human ingenuity itself. So how exactly do you look inside a 2,000-year-old computer without breaking it apart? This question has driven researchers to some extraordinary places, pushing the boundaries of both archaeology and physics in ways the original Greek craftsmen could never have imagined. When we last left our bronze mystery, traditional methods had taken us as far as they could go. X-rays had revealed the basic structure, but the mechanism's secrets remained locked inside layers of marine concretion, that rock-like coating formed by centuries of chemical reactions on the seafloor. To go deeper, researchers needed tools that didn't even exist when this investigation began. Enter the particle accelerator. You might be wondering how the same technology used to smash atoms apart could help us understand ancient gears, but it turns out that high-energy physics and archaeology make surprisingly good partners. At the European Synchrotron Radiation Facility in Grenoble, researchers placed fragments of the mechanism in the path of X-ray beams millions of times brighter than a hospital X-ray machine. The results were stunning. These synchrotron X-rays could penetrate the bronze and limestone concretion to reveal details invisible to conventional imaging. Suddenly, gear teeth that had been hidden for 2 millennia appeared in sharp relief. Inscriptions that were completely invisible to the naked eye emerged like ghost writing. We could see not just what the ancient Greeks had built, but how they had built it, the tool marks, the manufacturing techniques, even evidence of repairs and modifications. But reading the mechanism wasn't just about seeing it more clearly. It was about understanding it as a functioning machine. This is where 3D modeling entered the picture, transforming static images into dynamic reconstructions. research teams led by people like Tony Freeth at University College London began creating detailed computer models that could simulate how the mechanism actually worked. Think about what this means for a moment. We're using digital technology to resurrect ancient analog computing. Every gear ratio, every wheel position, every tiny inscription gets mapped in three-dimensional space and then brought back to life in virtual reality. Researchers can rotate dials that haven't turned in 2,000 years, watching as bronze planets dance through their calculated orbits. And then there's artificial intelligence, perhaps the most unexpected collaborator in this archaeological detective story. AI systems trained on thousands of images can identify patterns that human eyes might miss, the subtle variations in gear tooth spacing that reveal manufacturing techniques, or the faint traces of letters in inscriptions worn nearly smooth by time and sea. One of the most remarkable breakthroughs came when researchers used machine learning algorithms to help decipher the mechanism's instruction manual. Yes, you heard that right, this ancient computer came with instructions. Tiny Greek letters, barely visible even with synchrotron imaging, covered much of the mechanism's surface. These weren't just labels or decorations. They were a user's guide, explaining how to operate this bronze calculator of the cosmos. The AI didn't just read the letters, it helped researchers understand the context, identifying astronomical terms and cross-referencing them with known Greek texts about celestial mechanics. It was like having an ancient Greek engineer sitting alongside modern scientists, explaining how their masterpiece was meant to be used. But perhaps the most fascinating aspect of this digital archaeology isn't the technology itself, it's how it's changing our relationship with the past. Traditional archaeology often feels like looking through a keyhole, getting glimpses of ancient lives through fragments and ruins. With the Antikythera Mechanism, we're doing something different. We're having a conversation. Every new scan reveals details that let us ask better questions. Why did the craftsmen choose this particular gear ratio? How did they achieve such precise manufacturing without modern tools? What calculations were they running when the mechanism was set to specific dates? And as we answer these questions, we're not just learning about ancient Greek technology, we're learning about the fundamental human drive to understand and predict the natural world. There's something almost science fiction about it all. Ancient bronze gears being analyzed by particle beams, their secrets decoded by artificial intelligence, their functions simulated in virtual worlds. It's as if we've built a time machine, reaching back across 2 millennia to shake hands with the minds that created this marvel. And yet, for all our sophisticated technology, there's still so much mystery. We can see individual gear teeth with incredible clarity, but we still don't know exactly who made the mechanism or where. We can simulate its functions perfectly, but we're still discovering new capabilities hidden in its design. We can read its inscriptions with AI assistance, but the full meaning of its astronomical program continues to unfold. This brings us to something important about the nature of discovery itself. Each technological breakthrough, from X-rays to particle accelerators to artificial intelligence, doesn't just give us better tools. It gives us better questions. The mechanism isn't becoming less mysterious as we study it more deeply. In some ways, it's becoming more mysterious, revealing layers of sophistication that force us to completely rethink what ancient craftsmen and scholars were capable of achieving. The collaboration between ancient engineering and modern science is teaching us something profound about human creativity. The Greeks who built this mechanism weren't working with primitive tools and simple ideas. They were pushing the absolute boundaries of their available technology, solving complex problems with the same innovative spirit that drives modern engineers. The gear ratios they calculated, the mechanical solutions they developed, the user interface they designed, all of it demonstrates a level of technical thinking that we're only now learning to fully appreciate. As researchers continue to apply new technologies to the mechanism study, we're witnessing something unprecedented in archaeology, a complete reconstruction not just of an artifact, but of the knowledge system that created it. We're seeing how ancient Greek mathematics, astronomy, and mechanical engineering came together in a single device that was simultaneously practical tool and theoretical masterpiece. And that convergence of practical utility and abstract beauty? That might be the most modern thing about this ancient computer. But let's pause here for a moment and ask something that might seem obvious at first, but becomes more intriguing the longer we sit with it. What exactly makes the Antikythera mechanism a computer? When we use that word, computer, we're usually thinking of silicon chips and glowing screens, not bronze gears weathered green by 20 centuries underwater. Yet if we strip away our modern assumptions and look at what computation really means, the connection becomes unmistakable. A computer, at its heart, is any device that takes input, processes that information according to predetermined rules, and produces output. The input for our ancient Greek device was simple: you turned a crank to set a date. The processing happened through those precisely calculated gear ratios we've been exploring, each wheel turning at exactly the right speed to mirror the movements of celestial bodies. And the output? Dial readings showing where the sun, moon, and planets would be on any given day, when eclipses might occur, when the next Olympic Games would begin. This is analog computation in its purest form. Instead of the ones and zeros flowing through transistors in your smartphone, we have continuous rotational motion flowing through bronze gears. The mathematics is the same, it's just encoded in metal rather than electricity. When you adjust the brightness on your screen by sliding a control, you're using the same fundamental principle that ancient Greek craftsmen built into their mechanism over 2,000 years ago. Consider this: every time you use GPS navigation, your device is performing calculations remarkably similar to what the Antikythera mechanism did. Both systems track the positions of objects moving in predictable patterns, satellites in the case of GPS, celestial bodies for the mechanism. Both use that positional data to determine location and timing. Both translate complex mathematical relationships into something immediately useful for human navigation through space and time. The parallel becomes even more striking when we look at how modern devices handle periodic phenomena. Your smartphone's processor coordinates countless oscillating signals, radio waves, processing cycles, display refreshes, using principles that would be familiar to whoever designed the eclipse prediction capabilities of the ancient mechanism. They understood that complex periodic behavior could be broken down into simpler, predictable cycles that could be mechanically modeled. We might wonder, if the Greeks could build such sophisticated analog computers, why didn't they progress to digital systems? The answer lies partly in materials and partly in need. Bronze gears, however precisely crafted, have limitations. They wear down, they corrode, they can only be made so small. But they were perfectly suited to the astronomical calculations that mattered most to ancient Greek society. Digital computation had to wait for materials science to catch up with mathematical ambition. Yet in some ways, the Antikythera mechanism was more elegant than our modern devices. It was entirely self-contained, requiring no external power source beyond human hands. It could function for centuries without software updates or battery replacements. Its calculations were transparent, you could literally see the gears turning, watch the mechanical logic unfold before your eyes. There's something appealing about that directness, that physical manifestation of mathematical relationships. Today's computers have gained incredible speed and versatility, but they've lost that tactile connection between mechanism and meaning. When you swipe to unlock your phone, complex algorithms verify your fingerprint pattern, but the process is invisible, almost magical. The Greek device made its computations visible and comprehensible, a bronze manifestation of mathematical truth. This transparency extends to maintenance and understanding. If the Antikythera mechanism broke, a skilled craftsman could examine its gears, identify the problem, and repair it with bronze working tools available in any decent workshop. When your smartphone stops working, even the repair technicians often just replace entire circuit boards, treating the device as a sealed unit rather than a collection of understandable parts. But perhaps the most profound connection between ancient bronze and modern silicon lies in their shared ambition. Both represent humanity's drive to externalize our mental calculations, to build tools that extend our cognitive capabilities. The mechanism freed ancient astronomers from the tedium of manual calculation, just as modern computers free us from countless mental tasks. Both technologies transformed abstract mathematical knowledge into practical, interactive tools. We should also acknowledge what modern computation has gained. The Antikythera Mechanism, for all its sophistication, was specialized, built to model one particular slice of reality. Today's computers are general-purpose machines, capable of modeling anything from weather patterns to social networks to quantum mechanics. They've democratized computation in ways the ancient Greeks couldn't imagine. Yet there's something to be said for specialization. The mechanism was optimized for its specific task with an elegance that modern devices rarely achieve. Every gear had a purpose, every ratio was essential. There was no bloatware, no unnecessary features, just pure, purposeful functionality encoded in bronze. Contemporary engineers working on spacecraft or medical devices sometimes rediscover this principle, that true sophistication lies not in adding features, but in perfectly executing a focused purpose. As we hold our smartphones and tablets, marveling at their capabilities, we might remember that we're participating in a tradition that stretches back at least 21 centuries. The desire to mechanize calculation, to build thinking machines, to hold complex knowledge in our hands, these aren't modern innovations. They're deeply human impulses that found their first sophisticated expression in those corroded bronze gears pulled from Mediterranean waters. The Antikythera Mechanism reminds us that the relationship between human intelligence and mechanical assistance has always been collaborative rather than competitive. The ancient device didn't replace astronomers, it amplified their capabilities. Similarly, our modern computers work best when they enhance rather than substitute for human judgment and creativity. So the next time you check the time on your phone, or use a calculator app, or watch a planetary alignment app trace the movement of celestial bodies across your screen, you're participating in a conversation that began long before the age of electricity. The medium has changed from bronze to silicon, the scale has expanded beyond recognition, but the fundamental relationship remains the same, humans creating tools that think alongside us, helping us navigate the complexities of existence with greater precision and understanding. And in that continuity, we find something both humbling and inspiring about the persistence of human curiosity. And so we find ourselves at the end of this particular journey, but perhaps also at the beginning of something larger. You know, there's something almost poetic about the fact that the Antikythera Mechanism spent 2,000 years on the Mediterranean seabed, quietly waiting. Bronze gears slowly surrendering to salt water and time, yet somehow preserving enough of themselves to eventually tell their story. It makes you wonder what else might be down there, doesn't it? We've talked tonight about one artifact, one extraordinary machine that survived against all odds. But let's step back for a moment and consider the implications. If the ancient Greeks could create something this sophisticated, something that we're only now beginning to fully understand, what does that tell us about the nature of human knowledge itself? We like to think of progress as linear, don't we? Stone tools to bronze tools to iron tools to steam engines to computers. A neat progression where each generation builds directly on the last. But the Antikythera Mechanism suggests something more complex. It hints at peaks of understanding that might have been reached and then lost, entire traditions of knowledge that could vanish in the span of a few generations. Think about it this way, if not for that chance storm in 1901, if those sponge divers had taken shelter somewhere else, this device might still be sitting on the ocean floor. And we might never have known that such things were even possible in the ancient world. What other bronze computers are scattered across the Mediterranean? What other mechanical marvels lie buried under millennia of sediment and sand? The archaeological record is notoriously incomplete, after all. We estimate that less than 1% of all ancient artifacts have survived to the present day. Less than 1%. Which means that for every extraordinary object we do find, there might be 99 others that have been lost forever. Sometimes I think about the workshop where the Antikythera Mechanism was made. Picture it, ancient Greek craftsmen hunched over bronze blanks, carefully cutting gear teeth by hand, testing ratios, adjusting calibrations. There must have been apprentices learning the trade, masters passing down techniques, maybe even competing workshops creating their own versions. This wasn't just a one-off invention, it represents an entire technological tradition that we've only glimpsed through this single surviving example. And here's what really keeps me up at night: we know the mechanism was traveling on that Roman ship, probably as part of someone's personal collection or perhaps as a diplomatic gift. Which suggests these devices were being made, used, traded across the ancient world. They were part of the technological landscape of their time. So where are the others? Where are the instruction manuals, the backup copies, the improved versions? The silence is almost deafening when you really think about it. Entire civilizations have risen and fallen, taking their accumulated knowledge with them. The Library of Alexandria burning. The collapse of the Western Roman Empire. The destruction of Constantinople. Each of these events represents not just political upheaval, but the potential loss of irreplaceable scientific and technological understanding. Yet here's what I find most remarkable about the Antikythera Mechanism: it demonstrates that even when knowledge is lost, even when entire technological traditions disappear, the human capacity for innovation remains constant. Those ancient Greek engineers were working with the same fundamental curiosity that drives researchers today. They looked up at the night sky and asked the same questions we still ask. How does it all work? Can we predict what comes next? Can we build something that helps us understand? And they found their answer in bronze and calculation, just as we find ours in silicon and code. The tools change, the materials evolve, but the underlying impulse remains identical across millennia. We are a species that builds models of the world, that creates external representations of internal understanding. Whether it's scratching marks on bone to track lunar cycles 40,000 years ago, or programming quantum computers to simulate molecular interactions today, we're engaged in the same essential activity. The Antikythera Mechanism reminds us that we're part of a much longer story than we sometimes realize. Every smartphone in your pocket, every GPS satellite in orbit, every weather prediction algorithm, they're all descendants of that corroded bronze computer sitting at the bottom of the Mediterranean. Not direct descendants, perhaps, but spiritual ones. They represent the same fundamental human desire to hold complexity in our hands, to make the abstract tangible, to turn the vast movements of the cosmos into something we can understand and use. So what does the future hold? If ancient Greeks could create mechanical computers with hand tools and bronze, what might we accomplish with technologies they couldn't have imagined? If they could predict eclipses centuries in advance using gear ratios and mathematical insight, what predictions might we make with artificial intelligence and quantum computing? But perhaps more importantly, what will survive of our current technological moment? 2,000 years from now, what artifacts will future archaeologists puzzle over? Will they wonder how we managed to create devices that could access the sum total of human knowledge with a few taps of a finger? Will they try to reverse engineer our quantum computers from corroded fragments? The Antikythera Mechanism teaches us humility, I think. It reminds us that human ingenuity has always been extraordinary, even when working with seemingly primitive tools. It suggests that the gap between ancient and modern might not be as vast as we sometimes imagine. And it leaves us with questions that go far beyond archaeology or technology. As we drift toward the end of tonight's exploration, I want you to imagine looking up at the night sky the way those ancient Greek astronomers did. The same stars, the same planets, the same fundamental mysteries. They built their bronze computer to make sense of those celestial movements, to find patterns in apparent chaos, to hold time itself in mechanical form. And in doing so, they created something that speaks directly to us across 2 millennia, a message written in gear teeth and astronomical calculation, telling us that human curiosity is perhaps the most persistent force in the universe. More durable than bronze, more lasting than stone, more powerful than time itself. Thank you for joining me in the Twilight Archive tonight. Until next time, keep looking up, and keep wondering what other marvels might be waiting in the depths of time and sea.